A quiet cosmos stretches into eternity, a vast ocean of nothingness before light itself was born. There was no heat, no motion, no color, only potential, suspended in a stillness older than time. From that void came whispers of creation, subtle and unseen. Not stars, not galaxies, but forces more ancient than the first photon. The primal architects that would shape every birth, every death, every pulse of the cosmos. They are the unseen hands that built the universe, and perhaps one day will unravel it. Every atom in our bodies, every photon that carries a message across billions of light years, every second that ticks through the universe's memory is guided by these silent engineers. Gravity curves space itself, drawing matter into stars and galaxies. Quantum fields stir in the vacuum, spawning particles from nothing. Entropy marks the relentless march of decay. Dark energy pushes the cosmos apart, invisible yet overwhelmingly dominant. Together they compose the architecture of all that is and all that ever will be. Who designed this grand machine? What hidden symmetries, what unseen calculations govern its balance and decay? The universe is not chaos. It is a work of profound precision. Yet the architects remain hidden, their motives inscrutable, their presence known only through the perfection and fragility of what they have wrought. Through nebulae glowing with the birth of stars, across the collapse of massive suns into black holes, toward horizons where light itself bends and fades, the story unfolds. The cosmos is alive with the record of their influence, a narrative written in gravity, energy, and time. This is not merely the story of space and matter, it is the story of the architects themselves, the forces that shape existence, and perhaps have already set the blueprint for its ultimate end. There was a time when the universe was seen as eternal and unmoving, a celestial machine wound once by unseen hands and left to tick forever in silence. Humanity looked to the heavens and saw perfection, a realm untouched by change or decay. The stars appeared fixed, their patterns repeating endlessly across the sky, and so the ancients believed the cosmos itself was divine, unaltered since creation. The Greek philosophers called it the realm of ether, the purest form of existence. To them, motion and birth belonged to Earth, but the heavens were timeless. It was a comforting illusion, one that made the universe seem predictable, safe, and eternal. From these first stargazers came thinkers like Democritus, who imagined that all matter was composed of invisible atoms drifting through an infinite void. Yet even he believed that this motion existed within a greater stillness, a cosmic order that had always been. Centuries later, Isaac Newton gave structure to that dream. His laws of motion and gravity revealed a universe ruled by precise mathematical harmony. The stars, the planets, and the falling apple all obeyed the same invisible hand. To Newton, the cosmos was a perfect clock, built by a divine architect whose equations never faltered. Space and time were absolute, rigid, and eternal. Creation was finished. The universe was complete. For more than 200 years, this idea reigned unchallenged. Astronomers mapped the stars as if they were dots on a static canvas. Even as telescopes improved, the illusion of stillness endured. The Milky Way was thought to be the entire universe, its stars scattered through a serene and endless ocean. Beyond its edge, many believed there was nothing, but beneath this calm, deeper truths were stirring. In 1915, Albert Einstein published the field equations of general relativity. They were unlike anything science had ever seen. A vision of gravity not as a force, but as the curvature of space and time itself. According to Einstein's mathematics, space could bend, stretch, and ripple. It could change. The equations whispered something extraordinary. The universe was not static. It could expand or contract. It was alive. Yet the idea was too radical, even for Einstein. The universe, he believed, must be balanced, eternal, unchanging, perfect. To preserve that vision, he introduced a term that would haunt physics for a century: the cosmological constant, a mysterious force meant to counteract gravity and hold the cosmos in equilibrium. What Einstein could not have known was that this mathematical invention would one day resurface as one of the greatest mysteries in all of science, the phenomenon we now call dark energy. While Einstein was trying to keep the universe still, others were preparing to watch it move. In the 1920s, at the Mount Wilson Observatory in California, astronomer Edwin Hubble peered through the Hooker telescope. the most powerful eye ever built by human hands. What he found changed everything. Among the faint spirals of light that speckled the night, Hubble discovered entire galaxies, vast islands of stars far beyond our own. And more astonishingly, he noticed they were moving away from us. The light from these galaxies was stretched, shifted toward the red end of the spectrum. The farther away they were, the faster they fled. The data was undeniable. The universe was expanding. Space itself was stretching, carrying galaxies with it like leaves drifting apart on a rising tide. Suddenly, the illusion of stillness shattered. The cosmos was not a finished clock, but a breathing, evolving entity. It had a history, and perhaps a beginning. In the quiet halls of observatories, a new kind of awe emerged. The heavens were no longer perfect and eternal. They were restless, dynamic, alive with motion and change. The ancient notion of divine permanence gave way to something even more profound. A universe that could be born, could grow, and might one day die. The old architects, once thought to be gods, were replaced by the deeper architects of physics, forces and fields that shaped creation from the invisible fabric of space-time itself. For the first time in human history, we saw not a static masterpiece but an unfolding process. Each equation, each photon of light, each expanding galaxy revealed a pattern written into the cosmos long before life began. The universe had an architecture, not of marble and gold, but of gravity, light, and energy. Its walls were woven from mathematical laws, its pillars sculpted by invisible constants that determined the flow of everything from stars to atoms. This was the first true glimpse of the cosmic blueprint, a design both elegant and merciless, balanced between order and chaos. It suggested that the universe was not a random accident, but a system of profound logic, a self-creating machine built from its own laws. The realization was staggering. The age of cosmic architecture had begun. Humanity was no longer looking for divine hands to explain the heavens. The search had shifted toward the invisible frameworks of reality itself, the rules that govern existence. In the quiet hum of observatories and the chalk-covered walls of universities, a new kind of creation story was taking shape. And though we did not yet know it, the same equations that revealed creation's design would also whisper of its collapse. The architects of order were already there, hidden in the shadows of space-time, waiting to remind us that creation and destruction were never opposites, but parts of a single, endless plan. There is a silence older than sound itself. Before there were stars, before the first galaxies unfurled their spirals of light, the universe was a storm of heat and darkness, a cosmic ocean of particles too wild and too dense for light to move freely. For nearly 400,000 years after the Big Bang, the cosmos was a blinding fog, a plasma where photons were trapped in endless collision. Space was not yet transparent. Time itself seemed to breathe but not yet see. And then, one day, the fog began to clear. As the universe expanded, it cooled. The furious collisions slowed. Protons and electrons found one another and fused into atoms. The light that had been trapped for eons was finally released, free to travel, unbroken, across the newborn cosmos. That light still travels today, stretched and softened by billions of years of expansion. It is faint, almost imperceptible, but it fills all of space. In 1965, two radio engineers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, stumbled upon it. They were not searching for the origin of the universe. They were simply trying to eliminate a persistent noise from their antenna, a faint hiss that came from every direction, day and night. They cleaned the dish, chased away nesting pigeons, checked every wire, but the hum remained. What they had found was not interference. It was the oldest light in the universe, a whisper left over from creation itself. This faint radiation would come to be known as the cosmic microwave background, or CMB, the afterglow of the Big Bang. It was the first fossil of the cosmos, a map frozen in light, carrying the imprint of what the universe looked like when it was only 380,000 years old. Every photon of that background is a message from the beginning, an echo of the moment when the universe first became visible. To the human eye, this light is invisible, its wavelength too long to see. But to instruments orbiting high above Earth, satellites like COBE, WMAP, and later Planck, it reveals a tapestry of delicate variation. Tiny fluctuations in temperature, mere millionths of a degree, spread across the entire sky. These imperfections, once dismissed as noise, turned out to be the seeds of everything. Where the radiation was slightly warmer, matter was a little denser. Where it was cooler, the early universe held less mass. Over billions of years, gravity would magnify these subtle differences, pulling matter together to form stars, galaxies, and eventually, the cosmic web itself. It was as if the universe had spoken its first words. Soft, uneven, and full of meaning. A pattern that would later become structure, complexity, and life. But as scientists studied the CMB in greater detail, they noticed something unsettling. The pattern was not random. It was exquisitely ordered, with variations that fit within a narrow mathematical range. The temperature differences were almost too perfect, neither chaotic nor uniform, but balanced with uncanny precision. The question emerged, why this pattern and not another? To explain it, physicists turned their gaze toward the earliest fractions of a second after the Big Bang, a realm where known physics begins to dissolve. From this frontier came the theory of cosmic inflation, first proposed by Alan Guth in 1980. Inflation suggests that in the tiniest sliver of time after the Big Bang, less than a trillionth of a second, the universe expanded exponentially, faster than the speed of light. Space itself ballooned outward, smoothing out any initial irregularities and stretching microscopic quantum fluctuations to astronomical scales. In that unimaginable instant, quantum randomness became the blueprint for galaxies. Fluctuations smaller than atoms were pulled across light years of space, frozen as ripples in the fabric of reality. These ripples became the structure of everything that would ever exist. Inflation transformed chaos into order, an invisible hand sculpting the cosmos from the noise of quantum fields. The beauty of this theory lies in its elegance. Inflation explains why the universe looks so uniform in every direction, why the CMB's temperature is nearly identical across the sky, and why the geometry of space appears perfectly flat. It also predicts the exact kind of fluctuations the satellites would later observe, a match so precise that it turns speculation into one of the most powerful ideas in modern cosmology. And yet, with every answer came deeper mystery. Inflation solves many questions, but it raises others that are even more profound. What triggered this sudden expansion? What energy field powered it, and what stopped it? Did inflation happen only once? Or is it eternal, creating endless universes beyond our own? In the mathematics of inflation, space can spawn new regions faster than old ones stop expanding. An infinite fractal of universes, each with its own laws, constants, and architectures. Our cosmos might be only one bubble in an endless sea, a single verse in a grander cosmic song. The cosmic microwave background stands as the first page of that story, the universe's baby photograph, showing the moment it first took shape. Every tiny fluctuation we see today is a fossilized vibration of the quantum world, amplified to cosmic scale. Each point of light tells a story written when atoms did not yet exist, when even time itself was just learning how to flow. The CMB also carries subtle asymmetries, faint hints that the universe may not be perfectly isotropic. There are cold spots and alignments that stretch across vast regions, anomalies that defy the expected randomness. Some physicists speculate these might be scars, traces of collisions with other universes, or signatures of physics beyond our understanding. Others see them as statistical chance, but the mystery endures. In the soft hum of microwave radiation, the cosmos reveals both its simplicity and its strangeness, a perfect balance between order and imperfection, between the mathematical and the miraculous. It is a whisper that says, "I was born from chaos, and yet I remember my design." The discovery of the cosmic microwave background was more than an observation. It was a revelation, the first direct evidence that the universe had a beginning. It shattered the old belief in an eternal, unchanging cosmos and replaced it with a living, evolving one. For the first time, humanity had heard the echo of creation itself, a soundless resonance stretching across 13.8 billion years. The light discovered by Penzias and Wilson has now been measured with exquisite precision, revealing the universe's age, composition, and geometry. From it, scientists have learned that only 5% of the cosmos is made of ordinary matter, while the rest, dark matter and dark energy, remains invisible and unknown. Yet all of it, every galaxy, every particle, every heartbeat, owes its existence to the delicate variations frozen in that ancient light. When the universe spoke its first words, it did not speak in language, but in temperature and density, in quantum fields and expansion rates. Its vocabulary was written in the rhythm of physics itself. Those words became atoms. Those atoms became stars. Those stars became the elements of life. And as we listen to that ancient echo, captured in the faint microwave glow that still surrounds our planet, we realize that we are listening to the first sound the cosmos ever made. A whisper that has never stopped traveling, never stopped expanding, never stopped reminding us that creation began not with fire, but with a pulse of light finding its way through the dark. The Great Awakening had begun, the moment when the universe became visible, when chaos found order, and when the silent architects of the cosmos began to speak their plan into being. The deeper humanity looked into the workings of the cosmos, the more impossible it began to appear. Beneath the beauty of stars and galaxies lies a balance so precise that even the smallest deviation would have erased everything before it began. The universe, it seemed, was walking a razor's edge between existence and annihilation, a balance held together by invisible forces, each tuned with incomprehensible precision. Gravity, the architect of order, the sculptor of galaxies and worlds, is weak, astonishingly weak, a trillion times weaker than the electromagnetic force. If it were just a fraction stronger, the universe would have collapsed back upon itself long before the first stars could ignite. If it were weaker, matter would never have gathered at all. There would be no stars, no planets, no warmth, only an endless dark fog of drifting atoms. The strong nuclear force, the binding agent within every atomic nucleus, holds the very heart of matter together. If it were only 2% weaker, protons and neutrons would refuse to unite, and atoms as we know them would not exist. If it were slightly stronger, all hydrogen, the most abundant element in the universe, would have fused instantly into helium in the first seconds after the Big Bang. There would be no water, no stars like the sun, and no chemistry to sustain life. Even the electromagnetic force, which governs how atoms bond and light travels, seems balanced with astonishing precision. A minute difference in its strength would have destabilized atoms or prevented them from forming complex molecules. The same is true for the weak nuclear force, which allows stars to burn and forge new elements. If its rate were altered by the smallest degree, stars would not synthesize the carbon and oxygen necessary for life to emerge. And yet, here it is, a universe that works, a cosmos balanced on a knife edge of impossibility. This perfect orchestration became known as the fine-tuning problem, a revelation that shook the foundations of modern physics. The constants of nature, the speed of light, the gravitational constant, the Planck constant, the mass of the electron, appear fixed with values so exact that even a microscopic change would make the universe lifeless. The odds against such precision seem astronomical, almost absurd. Out of the infinite ways the laws of physics could have unfolded, only this narrow set of conditions allowed atoms, stars, and consciousness itself to exist. Was this balance the result of blind chance, or something deeper? For some, the numbers spoke of coincidence, a cosmic lottery that, against all odds, simply favored life. Others saw something more profound, as though the universe were aware of its own need for harmony. The philosopher and physicist Paul Davies described it as the impression of design, not divine necessarily, but purposeful, a structure that seemed to know the outcome before it began. Stephen Hawking wrestled with this paradox. He understood that the laws of physics allowed for infinite possible universes, yet ours seemed fine-tuned not just for stars and galaxies, but for observers capable of asking why. He once wrote, "The laws of science, as we know them, contain many fundamental numbers. The remarkable fact is that the values of these numbers seem to have been very finely adjusted to make possible the development of life." This raised an unsettling possibility that the universe, in some sense, knew we were coming. The concept is often captured by what scientists call the anthropic principle, the idea that the universe must have the properties necessary for life, because we are here to observe it. It does not demand design, only that we occupy a cosmos in which existence is possible. If the constants had been otherwise, there would be no observers to question them. It is a self-filtering truth, elegant yet deeply unsatisfying, for it explains everything while explaining nothing at all. But for others, the anthropic principle felt too passive, too convenient. It reduced the wonder of existence to mere selection bias. To thinkers like Max Tegmark, the question was not whether the universe was fine-tuned for life, but whether all possible universes exist, a vast multiverse, each with its own laws and constants. In such a landscape, life could only arise in the few universes where the conditions are right. We happen to inhabit one of those rare life-permitting worlds. If this is true, then the fine-tuning of our cosmos is no miracle, merely a statistical inevitability. But if the multiverse is false, if ours is the only universe that exists, then the question of why it is so precisely ordered becomes far more haunting. Physicists began to search for deeper explanations. Could there be an undiscovered theory, a theory of everything, that makes these constants inevitable? Some believe that quantum gravity or string theory might one day reveal hidden symmetries that explain the delicate balance of nature. Others suspect that what we call fine-tuning is an illusion born of incomplete understanding, a byproduct of a grander architecture still beyond human comprehension. The cosmological constant, the term Einstein once called his greatest blunder, is perhaps the most confounding example. It represents the energy density of empty space, a force responsible for the universe's accelerating expansion. Theoretical physics predicts that its value should be enormous, 10 to 120 times greater than what is observed. Yet the real value is so small, so precisely balanced, that it allows galaxies to form and persist. If it were even slightly larger, the cosmos would have torn itself apart long before life could take hold. To some, this discrepancy is the greatest fine-tuning of all, a number so improbable it seems almost deliberate. It is as though the universe were calibrated, one physicist remarked, to within 1 part in 10 to the power of 120. Such precision defies imagination. For the first time, the very laws of physics began to look less like inevitabilities and more like choices, parameters written into the code of existence. In that realization lies a deep and unsettling beauty. Creation itself begins to resemble an act of selection, as though reality has chosen to exist in the narrowest possible way that allows awareness to emerge. Every equation, every constant, every law appears to be part of an exquisite balance between chaos and order, destruction and creation. The architects of this balance, gravity, electromagnetism, the nuclear forces, seem to cooperate as if guided by some hidden symmetry. Even the randomness of quantum mechanics, when viewed from a cosmic scale, appears to produce a universe that favors complexity, and yet, no one knows why. Some physicists have compared the cosmos to a musical instrument, one string in a vast cosmic orchestra, tuned so precisely that even the smallest deviation would silence the melody. Others wonder if the harmony is real at all, if what we call fine-tuning is simply the only key in which life can be played. Still, the question endures, echoing through observatories, equations, and minds. Why does the universe exist in such a fragile balance between everything and nothing? Every atom, every breath, every star burning in the night sky owes its existence to a precision that defies chance. It is as if the cosmos itself were aware of the knife edge it walks, and in that awareness, chose to exist anyway. In that realization, science met philosophy once again. The universe, so vast and impersonal, began to look strangely intimate. A system not merely of matter and energy, but of meaning. The constants, those silent architects of creation, seemed to whisper from the equations. The universe should not have existed, and yet it does. The mystery deepened, and with it, the haunting thought that perhaps existence itself is not accidental, but inevitable, the only possible way for nothingness to remember what it means to be alive. In the silent depths of space, light carries memory. Faint, ancient, and stretched thin by time, it travels from the very dawn of creation, whispering secrets about the universe's first breath. To listen to this cosmic echo, humanity built instruments of extraordinary precision, observatories like COBE, WMAP, and Planck. Each one peered deeper into the sky, stripping away the noise of galaxies and dust, until only the afterglow of the Big Bang remained. The cosmic microwave background, a fossilized portrait of the infant universe. What they found was astonishing. This light, uniform at first glance, was not entirely smooth. It carried delicate ripples, subtle temperature differences, 1 part in 100,000, encoding the earliest seeds of structure. From these ripples, galaxies would form, stars would ignite, and planets would one day awaken to consciousness. The cosmic map revealed not chaos, but a hidden order, a blueprint of creation written in light. Yet, even in its order, there were anomalies. In the Planck data, a cold spot appeared, a vast region of space cooler than its surroundings, larger and deeper than statistical chance could easily explain. Elsewhere, alignments stretched across billions of light years, patterns that seemed to defy the randomness expected from the Big Bang. Some scientists called it the axis of evil, a mysterious orientation linking temperature fluctuations across the entire sky, as if the universe itself had a preferred direction, a subtle asymmetry written into its design. Were these mere coincidences, or clues, remnants of a deeper structure beneath the surface of known physics? The anomalies refused to disappear. Some cosmologists suggested they were artifacts, the result of cosmic variance, statistical, noise, or even the interference of local structures like supervoids. Others dared to imagine something far grander, that these strange imprints were footprints of other universes, faint gravitational bruises left by collisions in a vast multiverse. In this view, our universe is not alone, but one bubble in an infinite, cosmic sea, each expanding into its own reality, each governed by different physical laws. If two such bubbles ever touched, the collision might leave a faint scar across the cosmic background, a cold region, a ripple, a whisper from another cosmos brushing against our own. The Planck satellite's maps hinted that such a story might be written into the microwaves that fill our sky, but if true, it would mean that our entire existence is just one verse in an eternal symphony of universes, and the blueprint we seek may stretch far beyond our cosmic horizon. To decode this blueprint, physicists turned inward, not into space, but into the quantum realm, the invisible machinery of reality itself. What they found was even stranger than the anomalies in the sky. At the smallest scales, space is not empty. It seethes with restless energy, a foam of creation and destruction. Even in perfect vacuum, quantum fields fluctuate constantly, spawning virtual particles that flicker into existence only to vanish again. This invisible storm of activity, known as vacuum fluctuations, is the heartbeat of the cosmos, the raw fabric from which everything emerges. According to quantum field theory, every particle, every force, every bit of matter is a vibration of these fields. Reality, then, is not built from solid things, but from oscillations in an ocean of potential. The universe is less a structure and more a song, a resonance sustained by the trembling of the void. This revelation reshaped cosmology. It suggested that the Big Bang itself might have been ignited not by something, but by nothing, by a fluctuation in the quantum vacuum that inflated into a universe. From a tiny patch of space-time, smaller than an atom, energy surged outward, space itself expanding faster than light, smoothing the universe into near-perfect uniformity. And within that expansion, tiny quantum ripples were stretched to cosmic scales, the very fluctuations that COBE, WMAP, and Planck would one day map as the birthmarks of the universe. These were the fingerprints of quantum physics written across the sky, proving that the architects of structure were not divine, but quantum, randomness itself, frozen into pattern. But this understanding only deepened the mystery. For if the vacuum is never truly empty, what lies beneath it? What field or law gives rise to this endless motion? The vacuum energy, when calculated by quantum mechanics, is staggeringly large. So large that, if real, the universe would have torn itself apart. Yet, when measured by astronomers, it is nearly zero, balanced so delicately that it allows galaxies to exist at all. This discrepancy, known as the cosmological constant problem, is one of the greatest unsolved puzzles in science. It is as though nature hides its own foundation, cancelling its infinite energy almost perfectly, leaving just enough residue to shape cosmic history. In that faint residue, physicists see the traces of something profound, a link between the smallest and largest scales, between quantum chaos and cosmic order. The blueprint of reality, it seems, might not be written in matter, but in fluctuation, a pattern of uncertainty that gives rise to everything. Some scientists imagine the vacuum as a quantum ocean, an eternal sea that births universes like waves. Each fluctuation could spawn a new cosmos with different constants, different laws, different destinies. In such a picture, our universe is not unique, merely one realization among infinite possibilities. The cold spot, the alignments, the strange whispers in the CMB might be faint ripples from those other shores, echoes from neighboring realities brushing against our own. Others propose that the blueprint is more fundamental still, that the laws of physics themselves are emergent, not imposed from above, but arising naturally from the self-organizing behavior of the quantum vacuum. In this view, there were no architects, only patterns that built themselves, the universe learning to exist. But if the cosmos can emerge from the void, if something can arise from nothing, what does nothing truly mean? Quantum theory suggests that emptiness is an illusion, that even the absence of matter is alive with potential. The deeper we look, the less solid reality becomes, as though existence itself were a mirage shimmering above a sea of uncertainty. And yet, through this uncertainty, a structure persists. From the smallest quantum tremor to the largest galaxy cluster, the same mathematical symmetries echo, self-similar, recursive, beautiful. The cosmos appears not random, but relational, every part connected by invisible threads of cause and pattern. As the Planck satellite shut its eye and the final maps were drawn, the image that emerged was both humbling and haunting. It showed a universe born from nothing, yet filled with precision, disorder sculpted into order by fluctuations no one can see. The blueprint was there, faint, fragmented, and mysterious, written in the very noise of the void. The question that remains is no longer how the universe began, but why the laws that govern it seem perfectly designed for it to begin at all. The deeper science peers into the cosmic fabric, the more it senses that what we call nothing might be everything, and that hidden within the silence between particles lies the echo of creation itself. The search for the blueprint continues, but each discovery blurs the boundary between chaos and design, chance and intention. Perhaps the architects of the universe were never beyond it, but within it, encoded in the vacuum, in the trembling fabric of space, in the endless conversation between uncertainty and existence. For now, the cosmos remains both map and mystery, a masterpiece of invisible geometry, still unfolding, still whispering its first words across the cold, eternal dark. For most of the 20th century, the story of the cosmos seemed simple enough. The universe had begun in a fiery explosion, the Big Bang. And ever since, gravity had been pulling everything back together. Galaxies formed, stars were born, and over billions of years, the cosmic expansion was expected to slow, perhaps even reverse, collapsing everything back into a final inferno, a mirror image of creation. But at the end of the century, the universe whispered something no one expected. In 1998, two teams of astronomers, the Supernova Cosmology Project and the High Z Supernova Search Team, studied distant stellar explosions, type Ia supernovae, scattered across the deep sky. These dying stars, uniform in brilliance, served as cosmic yardsticks, revealing how fast galaxies were moving away. The results were unmistakable and terrifying. The expansion of the universe was not slowing, it was accelerating. This discovery overturned the foundation of modern cosmology. A force stronger than gravity, stranger than any known energy, was pushing galaxies apart, an invisible agent of expansion that seemed woven into the very fabric of space-time. In its wake, the grand vision of a universe governed by predictable decay collapsed into uncertainty. The cosmos, once thought to be winding down, was instead racing away from itself. The discovery reawakened an idea Einstein had once tried to erase. In 1917, he had introduced a mathematical term, the cosmological constant, denoted by the Greek letter L, to to balance his equations and keep the universe static. When Hubble's discovery of expansion rendered it unnecessary, Einstein reportedly called it his greatest blunder. But the supernova data suggested that his discarded term might not have been a mistake at all. It might be the most profound insight ever written into physics, a fingerprint of the very force driving the cosmos apart. This invisible pressure came to be called dark energy. It could not be seen or touched, yet its influence was everywhere. It accounted for nearly 68% of the entire energy density of the universe, more than all matter, light, and radiation combined. It did not shine like stars or gather like galaxies. Instead, it stretched space itself, filling every void, multiplying distance with every passing moment. The revelation was staggering. For centuries, human science had been built on the study of matter, on what could be touched, measured, or illuminated. But now, it seemed that the majority of reality was made of something we could not perceive at all. Dark energy defied the imagination of even the greatest minds. It was not a force in the usual sense, like gravity or electromagnetism. It could not be localized or shielded. It behaved not as a substance, but as a property of space itself, an intrinsic energy that increased as the universe expanded. Every cubic meter of vacuum carried a constant, infinitesimal amount of this energy, and as space grew, the total grew with it. In this sense, the universe was not merely expanding into emptiness. Emptiness itself was expanding. Cosmologists searched for explanation in the known frameworks of physics, but none seemed to fit. Quantum field theory predicted that even the vacuum should teem with energy, a frothing sea of virtual particles. Yet the energy it implied was 120 orders of magnitude greater than what observations revealed. It was the most extreme mismatch between theory and measurement in all of science, a numerical wound in the structure of physics. Itself, something was missing. Some suggested that dark energy might be Einstein's cosmological constant after all, a fixed property of the vacuum, small but non-zero, destined to dominate forever. Others proposed a more dynamic agent, a changing field that evolves with time, dubbed quintessence, echoing the ancient philosopher's fifth element. Still others speculated that what appeared to be acceleration was an illusion, born from unseen structures or a fundamental misreading of gravity's laws. But with every new observation, the evidence only deepened. Measurements of the cosmic microwave background from the Planck satellite confirmed that dark energy was real. The vast cosmic web, mapped through galaxy surveys, showed its signature in the way matter clustered and thinned over billions of years. Even the light of the earliest quasars bent slightly more than it should, tracing the faint curvature of a universe increasingly dominated by something unseen. The implications were cosmic in scale and existential in tone. If dark energy continued its work unchecked, the universe would never collapse. Gravity would never reclaim its dominion. Instead, space would stretch faster and faster, galaxies drifting beyond visibility, their light fading into red oblivion. Stars would burn out one by one, leaving only the cold embers of matter in an ever-expanding void. This was not the serene eternity once imagined by philosophers, nor the cyclical rebirths envisioned by ancient cosmologies. It was a slow unraveling, a cosmic isolation, a heat death, the eventual extinguishing of all structure, all motion, all light. The same force that had sculpted creation now seemed to be drafting its end. It was as if the universe had been designed to rise, flourish, and fade, guided by a principle both creative and destructive. The architects of creation, those unseen laws that had balanced the forces of matter, radiation, and gravity, were also revealed as architects of dissolution. Their masterpiece was self-consuming, a vast, expanding cathedral destined to collapse not inward, but outward into silence. Physicists struggled to comprehend this duality. Could dark energy be the echo of the Big Bang itself? A lingering pressure from the universe's first moment, still driving it outward? Or was it something deeper, a sign that space and time are not final, but emergent, born from quantum processes beyond our comprehension? Stephen Hawking once mused that discovering what dark energy truly is might require a new understanding of reality itself, a theory that unites quantum mechanics with relativity. In that union might lie the ultimate truth of existence. why the universe began, why it expands, and whether its story must end in isolation or rebirth. Yet the more science learns, the more this mystery deepens. Dark energy is not a distant curiosity. It is the background against which everything happens. It is the silence between galaxies, the breath of expansion, the hidden rhythm of cosmic time. It is the invisible architect still at work, writing the fate of stars in the language of geometry. Perhaps it is not the antithesis of creation, but its continuation. The same energy that once tore matter apart, now carrying the universe toward its final equilibrium. A balance so delicate, so incomprehensibly precise, that it borders on the miraculous. In the accelerating dark, galaxies drift like lanterns carried by a wind no one can feel. Space stretches, time slows, and the cosmos, once thought to be eternal in its stillness, is revealed to be a living, breathing entity, expanding, aging, and moving toward an unknown horizon. The forgotten constant, the term once dismissed as a mistake, has become the key to everything. It is the heartbeat of the void, the hidden hand that guides both beginning and end. Dark energy, silent and unseen, now rules the universe. And in its quiet dominion lies the greatest paradox of all, that the same force which birthed the stars will one day ensure that none remain to see them. In the silence that follows discovery, science turns inward. It begins to ask questions that border on the sacred. Not just how the universe works, but why it works the way it does. After dark energy's unveiling, cosmology entered its most speculative age, an era of imagination grounded in mathematics, where physicists tried to name the unseen architects shaping reality. Each theory offered a different vision of creation, a different story of the hidden hands guiding the cosmos. The first, and perhaps simplest, was the vacuum energy model. It proposed that dark energy is not a force, nor a field, but a property of space itself, the energy of the vacuum. Even in the absence of particles, the void seethes with quantum fluctuations, tiny ripples in the fields that underlie all existence. These fluctuations give rise to a residual energy, uniform and eternal, woven into the geometry of space-time. In this view, the expansion of the universe is not being driven by something external. It is a natural consequence of what empty space is. The vacuum is not nothing. It is an ocean of restless potential. Every cubic centimeter of space carries a faint hum of energy, and as the universe grows, the total energy increases. Expansion becomes self-sustaining, a quiet feedback loop built into the foundation of reality. But this idea carries a contradiction that has haunted physicists for decades. When quantum theory calculates the vacuum's energy, it predicts a value so large that it would have torn the universe apart before atoms could even form. A trillion times greater than what astronomers actually observe. It is the greatest mismatch between theory and reality ever recorded, a wound that refuses to heal. To some, this mismatch hints that we are missing something profound, that vacuum energy is not static at all. Thus arose a new contender, quintessence. Quintessence imagines dark energy not as a fixed property, but as a dynamic field, evolving over cosmic time. Like a tide that shifts its rhythm, it could have been stronger in the past, weaker in the future. Its energy may flow, oscillate, or decay, altering the fate of the universe in ways still unseen. If true, dark energy might not be eternal. It could fade, reverse, or even transform into a new force altogether. The name quintessence comes from the ancient world, the fifth element, beyond earth, air, fire, and water. It was once believed to fill the heavens, to bind the celestial spheres. Now, modern science resurrects that ancient idea, giving it form in equations instead of myth. In this vision, the universe is alive with a breathing energy, a field that evolves as the cosmos matures, perhaps with its own hidden symmetry, its own pulse of existence. But if these models describe the internal rhythm of our universe, others dare to look beyond, to what might lie outside the cosmic stage entirely. Here, speculation enters its most audacious form, the multiverse theory. According to this idea, our universe is not unique, but one bubble in an infinite cosmic sea, a vast multiverse where each bubble carries its own set of physical laws, constants, and dimensions. In some, gravity might be stronger. In others, stars might never ignite. Each universe expands, collides, or vanishes, playing out a variation of cosmic possibility. The implications are staggering. The fine-tuning that makes life possible in our own universe, the delicate balance between the forces of nature, might not be a miracle at all, but simply a selection effect. In an infinite landscape of universes, some were bound to get the recipe right. We exist in one of those rare bubbles where conditions align just enough for matter, structure, and consciousness to emerge. This reasoning, known as the anthropic principle, suggests that the universe appears perfectly calibrated for life simply because, in all others, there was no one to notice. But for many scientists, the multiverse is a troubling escape hatch, an idea that can explain everything and therefore predicts nothing. There is, as yet, no way to see beyond our cosmic horizon. No telescope can peer into another universe. If others exist, their light will never reach us. The multiverse remains both tantalizing and unreachable, a theory suspended between mathematics and faith. Still, some of its echoes may hide in the structure of our own universe. Collisions between neighboring cosmic bubbles could leave subtle imprints, scars in the cosmic microwave background, or strange gravitational patterns frozen in space-time. Some anomalies in the Planck data, faint and unresolved, have been whispered to match such signatures. If confirmed, it would mean that the birth of our universe was not an isolated event, but part of a grander cosmic lineage, universes giving birth to universes, an infinite architecture beyond all comprehension. But if expansion is driven by a vacuum energy, and if that vacuum is unstable, then another possibility emerges, one far more unsettling. Physicists call it false vacuum decay. According to quantum field theory, the vacuum state we live in, the very foundation of space, may not be the true ground state of reality. It could be a metastable condition, balanced on the edge of collapse. Like a ball resting in a shallow valley, the universe appears stable, yet a deeper valley may lie beyond. A lower energy state waiting in the unseen depths of the field. If a quantum fluctuation ever pushed a small region of space into that deeper valley, it would trigger a catastrophic chain reaction. A bubble of true vacuum would form and expand at nearly the speed of light, rewriting the laws of physics as it consumed everything in its path. Atoms, stars, and even space-time itself would be redefined in an instant. No warning, no escape, just transformation. This possibility, though horrifying, emerges naturally from the mathematics of our best theories. Some calculations suggest that the Higgs field, the field that gives mass to particles, may place us dangerously close to this edge. If so, the universe's apparent calm is an illusion, a fragile equilibrium maintained by chance and time. Yet even in this terrifying vision lies a strange beauty. The architects of creation and destruction are not gods or beings, but fields, silent, omnipresent, and eternal. They sculpt reality not through intention, but through interaction. They whisper the language of symmetry, energy, and decay. And as science ventures deeper into these mysteries, it finds itself standing between two great pillars of human understanding, quantum mechanics and general relativity. One describes the subatomic realm, where uncertainty rules and space dances with probability. The other governs the grand structure of space-time, where gravity bends light and time itself flows. Each is magnificent, each is incomplete. Together, they refuse to merge. At the heart of dark energy, their conflict becomes absolute. Relativity paints a smooth, continuous universe. Quantum theory reveals one that flickers and foams. Between these visions lies the deepest rift in science, the split between the very large and the very small. To bridge it, physicists turn to string theory and loop quantum gravity, two monumental attempts to weave a single tapestry of all existence. String theory envisions the universe as a symphony of vibrating strings, each resonance giving birth to particles, forces, and dimensions. In this view, the architects of the cosmos are musical. Their creation, a vibration resonating across hidden dimensions beyond our perception. Loop quantum gravity, by contrast, imagines space-time itself as granular, woven from tiny loops of energy, like a cosmic fabric stitched from the quantum. Time and space, in this theory, are not continuous but pixelated, quantized at the smallest possible scales. Both theories glimpse the architect's workshop, the hidden geometry where quantum and gravity intertwine. Yet neither opens the door. Every attempt to merge the equations, to reveal the master blueprint, ends in paradox or uncertainty. Perhaps the universe guards its secret because the secret is not singular. The cosmos may be built not from one architecture, but from many overlapping designs, each a fragment of a larger, unknowable whole. And so physics continues its search across scales and centuries. From the trembling of quarks to the stretching of galaxies, it listens for the echoes of the architects beyond the horizon, those unseen forces that shape everything yet reveal nothing. The blueprint remains sealed. The deeper the universe is understood, the more it seems to hide. Still, through the cracks of comprehension, light escapes, faint, fragile, and profound, reminding humanity that even if the architects remain unseen, their work surrounds us. Every atom, every law, every breath of space and time is part of their silent design. The universe does not speak in words. It speaks in light, in gravity, in the silent geometry of space-time itself. To understand its message, humanity builds instruments that act as translators, machines that stretch the limits of perception, turning faint whispers from the cosmos into measurable truth. Each telescope, each detector, each collider is an extension of the human mind, reaching across billions of years, asking the same ancient question: what is the design behind all this? The James Webb Space Telescope was born from that question, a golden eye unfolding in the cold darkness, its mirrors opening like petals of precision and patience. Suspended nearly 1 million miles from Earth, it stares backward in time, capturing light that has traveled since the dawn of galaxies. Through its infrared gaze, Webb observes the first luminous structures that emerged after the cosmic dark ages. The earliest galaxies, still shrouded in hydrogen fog. Each of those galaxies is a fossil of creation, revealing how matter gathered, how stars ignited, and how gravity sculpted the first blueprints of order. But Webb's deeper purpose is not only to witness light, it is to test the theories that govern it. The inflationary model, the idea that the universe expanded faster than light in its first fraction of a second. If the patterns Webb observes in those primordial galaxies match the imprints predicted by inflation, then humanity will have peered into the first pages of the cosmic manuscript. Yet even as Webb looks backward, other eyes turn outward. To the accelerating cosmos of today, the Euclid mission, launched by the European Space Agency, scans the sky to map the subtle distortions of light caused by gravity, the warping of space-time itself. By observing how galaxies cluster and stretch over cosmic distances, Euclid traces the fingerprints of dark energy across billions of light years. It measures not the visible, but the invisible hand that governs the expansion of all things. At the same time, on the Chilean mountainside, the Vera C. Rubin Observatory prepares to begin its grand survey, photographing the entire visible sky every few nights. Its vast digital eye will capture motion, change, and time itself. Over 10 years, it will assemble the largest cinematic record of the universe ever created. Billions of galaxies, countless stars, and the slow drift of cosmic structures as they expand under the influence of dark energy. Together, Euclid and Rubin form a new kind of observatory, not of light, but of evolution. They will chart the universe not as it is, but as it becomes. While these telescopes explore the vast, others turn to the infinitesimal, to the hidden realms of quantum fields that might contain the secret to cosmic expansion. Beneath the soil of Switzerland and France, the Large Hadron Collider continues its search for what lies beneath known physics. Within its 27-kilometer ring, protons collide at energies that recreate the universe's first microseconds. Here, physicists hope to glimpse the subatomic architects, hypothetical particles or fields that could link the forces of the quantum world to the dark energy that shapes the cosmic one. Supersymmetry, hidden dimensions, quantum vacuum interactions. Each experiment is a question cast into the void, each data point a possible whisper from the architects themselves. And yet, the collider's discoveries have so far deepened the mystery. The Higgs boson was found as predicted, but beyond it, silence. No supersymmetric partners, no new particles. The emptiness speaks louder than discovery, as if the universe hides its mechanisms behind a curtain of symmetry too perfect to disturb. Still, the search continues, expanding not just outward or inward, but through space-time itself. In 2015, humanity heard the universe in a new way. From a pair of black holes colliding over 1 billion light-years away came a tremor, a gravitational wave rippling through the fabric of existence. Detected by LIGO and later confirmed by Virgo, it marked the first time space-time itself had spoken directly. These ripples are not sound, but motion, distortions in the geometry of reality traveling at light speed. Each wave carries the signature of a cosmic event. Black holes merging, neutron stars collapsing, space-time bending upon itself. Yet some physicists believe that hidden within these waves could be the echoes of the first expansion. Faint vibrations left over from the Big Bang's inflationary burst. If detected, those primordial waves would reveal the fingerprints of creation, not just what the universe is made of, but how it came to be. It would be like hearing the first heartbeat of time itself. Now, as detectors grow more sensitive, humanity is building the next generation of instruments. LISA, the Laser Interferometer Space Antenna, will drift in the quiet vacuum of space, using 3 spacecraft linked by laser beams millions of kilometers apart. It will listen for gravitational waves too long to be heard on Earth, the low, deep symphony of colliding galaxies and orbiting supermassive black holes. And beyond that horizon, even newer technologies are emerging. Quantum sensors, cooled to near absolute zero, can detect minute distortions in the vacuum, potential traces of dark energy's interaction with the quantum world. 21-centimeter sky surveys trace the faint glow of hydrogen stretching across cosmic time, mapping the web-like structure of the universe with unprecedented detail. Neutrino detectors buried deep under ice and rock wait for particles that carry messages from the earliest epochs, passing through entire planets as if through mist. Every new instrument adds a verse to the same cosmic poem, each built to catch a signal that may never come, each one refining the question rather than the answer. And yet, the more the instruments see, the more elaborate the design appears. Galaxies arrange themselves in filaments like neurons in a cosmic brain. The cosmic web pulses with structure and balance, its vast emptinesses as intentional as its crowded clusters. The deeper the mapping, the more the universe resembles an equation written with purpose, elegant, efficient, and impossibly precise. Dark energy's influence appears uniform, constant, unwavering across time. As if the expansion follows a plan too steady to be random, the forces that sculpt matter, from quantum to cosmic scales, seem tuned in delicate proportion. Slightly stronger and stars would never form, slightly weaker, and atoms would drift apart. It is as if the cosmos knows itself, not consciously, but through laws so coherent they mimic intent. In laboratories and observatories, humanity stands before this silent intelligence. Each photon captured, each equation tested, is another line drawn in the grand reconstruction of the cosmic blueprint. With each discovery, the boundary between observer and participant begins to blur. The act of observing reshapes understanding, and understanding reshapes the observer. In studying the cosmos, humanity becomes part of the same unfolding pattern it seeks to comprehend, a self-aware filament of matter, briefly illuminated by the very forces it tries to decode. The instruments of science do more than record data. They allow the universe to know itself through us. From the deep sky to the quantum vacuum, from gravitational waves to invisible energy, every experiment is a mirror held to creation, and the reflection staring back is not separate from it. The search continues, across time and distance, across the seen and unseen, and though the blueprint remains hidden, its outline grows sharper with every question. Somewhere between the noise and the silence, between the galaxies and the void, the design waits, not to be revealed all at once, but to be understood piece by piece, by those who dare to look into the dark and see meaning written in the stars. In the beginning, the universe was born in a burst of light and motion, an eruption of energy so complete that even time itself was set ablaze. But hidden in that first expansion was something more profound than birth. Encoded in the very equations that shaped creation was the seed of its demise. The cosmos did not simply begin, it also began to end. Every star that burns carries within it the mathematics of its own collapse. Every galaxy that spins will someday slow. Every photon racing through space contributes to the great dispersal, the gradual thinning of existence. The universe, for all its brilliance, has always been a story of entropy. Entropy, the silent accountant of decay, measures the universe's loss of order. From the first instant of creation, it began its work. With every collision, every fusion, Every life that flickers and fades, entropy grows. It is the shadow of time itself, following light wherever it goes. For centuries, humanity has tried to read this cosmic balance sheet, to understand not only how the universe began, but how it might end. Today, physicists trace that fate to the same mysterious force that drives the cosmos outward: dark energy. Discovered at the turn of the millennium, this invisible expansionist rules the future as it once ruled the past. Its presence fills all of space, accelerating the separation of galaxies, pushing matter away from matter, silence away from sound. It is as if creation itself is still unfolding, but in reverse, toward isolation instead of unity. What will happen if this expansion continues unchecked? If dark energy grows stronger with time, the universe will not merely expand, it will tear itself apart. Galaxies will drift beyond one another's horizons. Stars will vanish from view, their light stretched into invisibility by the accelerating fabric of space-time. Eventually, even the gravitational glue that binds solar systems will fail. Planets will drift free, stars will unravel. Atoms themselves will come undone as the repulsive force overwhelms every bond of nature. This is the Big Rip, a cosmos shredded by its own expansion. In this scenario, space does not simply grow, it fractures. The distances between particles increase faster than any light could cross them. The universe ends not in fire, but in disintegration, an ultimate isolation where even the laws of physics dissolve. But perhaps dark energy will not strengthen. Perhaps, like a fading ember, it will weaken with time. If it decays, gravity, the old architect of structure, will rise again. The expansion will slow, the outward rush will halt, and then the fall will begin. Galaxies will draw together once more, merging in immense cosmic collisions. Black holes will swell, devouring the light around them. The universe will contract, growing hotter and denser as it rewinds the film of creation. The stars of the future will be born not in the vacuum of expansion, but in the crush of collapse. This is the Big Crunch, a mirror image of the Big Bang, a closing symmetry written into the same equations that once opened the universe. Space would fold upon itself, time would lose direction, and all energy, all matter, all memory would converge into a single, dense singularity, a final heartbeat echoing the first. And yet, between these extremes lies a quieter, colder fate. If dark energy remains perfectly balanced, neither growing stronger nor fading away, the universe will continue expanding forever, but slowly, steadily, toward exhaustion. Stars will burn out, new stars will no longer form, galaxies will drift into invisibility, black holes will dominate, swallowing the last traces of light, but even they will not last. Over unimaginable epochs, black holes will evaporate through Hawking radiation, bleeding energy into the void. When the final one fades, the cosmos will be left in a uniform haze of faint particles, a sea of near-nothingness spread across an ever-expanding desert of space. This is the heat death, the universe's silent eternity. A cosmos without contrast, without motion, without memory. Entropy will have reached its maximum, and with it, time itself will lose meaning. No process will remain to mark change. The universe will become a perfect, unbroken stillness. In this end, there is neither fire nor collapse, only equilibrium, a balance so complete that it becomes indistinguishable from oblivion. But whichever fate awaits, rip, crunch, or heat death, all are written in the same primordial equations. The constants that allowed the first atoms to form are the same that determine the last to decay. The cosmic architects, those delicate relationships between energy and gravity, pressure and expansion, creation and entropy, have scripted both genesis and ruin into a single story. For every moment of creation contains the architecture of destruction. The hydrogen that fuels the first stars is born to be consumed. The forces that draw matter together also tear it apart. Even the dark energy that pushes galaxies outward may one day ensure their undoing. It is a paradox that defines existence itself. The same laws that create beauty also guarantee its impermanence. In the quiet reflection of cosmology, this truth emerges with both awe and melancholy. The universe is not a static monument. It is a process, a movement, a continual transformation from order to chaos, from light to darkness. Entropy does not destroy meaning, it creates it. Without decay, there could be no evolution. Without time's arrow, no becoming. Every collapse is a continuation. The universe folding itself into new expressions of the same eternal laws. And so, the story of creation has always been the story of collapse. Not a tragedy, but a cycle. A self-sustaining rhythm in which birth and death are one. The cosmic architects did not design permanence. They designed continuity. In this light, the end is not an erasure, but a return. A closing of the loop that began in the first spark of the Big Bang. Whether it ends in fire, in silence, or in infinite fragmentation, the universe will fulfill the equation it began with. The same physics that built the stars will one day unmake them. The same energy that ignited creation will extinguish it. And yet, in that balance, in that perfect symmetry between beginning and end, lies the most profound revelation of all. That existence, in every form, is temporary only because it is complete. The architects of creation are also the architects of dissolution. Their design was never to preserve, but to evolve, to let light bloom, fade, and return to darkness, so that the universe could be not eternal, but alive. And in that grand continuity, the end written in the beginning is not a conclusion. It is a whisper, returning to the silence from which everything first began. In the vast expanse of space, where galaxies drift like islands in a dark ocean and time stretches beyond comprehension, there lies a profound question. Not of matter or energy, but of consciousness itself. Perhaps the architects of the cosmos were never external forces at all, but the universe reflecting upon its own existence. The laws of physics, the constants that guide every atom, every photon, every pulse of space-time, may be the universe's self-awareness made manifest. Structures arising not by accident, but because they could be observed, because they allow the cosmos to perceive itself. Every star that ignites, every galaxy that spirals, every ripple in the cosmic microwave background is both creation and record. The universe is a mirror, reflecting back not only the presence of observers, but the possibility of understanding. Carl Sagan once said, "We are a way for the universe to know itself." Perhaps we are more than that. Perhaps we are the instruments through which the cosmos remembers creation and collapse are no longer opposites, but movements in a single, eternal rhythm. The Big Bang and the heat death, the Big Crunch and the Big Rip, are variations of the same underlying pulse. The universe breathing in and out, expanding and contracting, folding light and darkness into a pattern that repeats across scales, across eons. Entropy does not erase meaning, it transforms it. Energy and matter dance between order and chaos, between being and nothingness, in a rhythm older than the first photons, older than time itself. The architects, those hidden forces that guided expansion and sculpted structure, are forgotten only because we are their living memory. Every thought, every observation, every act of understanding is an extension of their work. We carry within us the equations of creation, the quantum fluctuations that seeded galaxies, the gentle push of dark energy that will one day stretch the cosmos into silence. In observing, measuring, imagining, we become both witness and participant, the final notes in a symphony composed over 13 billion years. As the stars fade and the universe drifts toward entropy, a question lingers in the dark. Were we always the architects, shaping and remembering in equal measure? Or are we the final dream of forces too vast to name? A fleeting reflection of an eternal design. And in that silence, as the cosmos stretches outward into infinite night, the universe waits, remembering itself through the eyes that can behold it.